Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.
The story I'm going to tell you today plays in Bern, Switzerland. Bern is the capital of Switzerland, is in the heart of Europe, and exists for over 800 years. It's considered one of the most beautiful cities. This is this spring in Bern, one of the most beautiful cities. It's located close to the river, the Arbor, that comes from the nearby mountains. And the city is really enclosed in a U-shaped river bend, which of course in medieval times was fantastic because that river provided protection from three sides. The city houses 150,000 people, and of course because of the growth of the city, it's spilled beyond that river bend and really goes up to the nearby mountains now. To outsiders, Bern is known for its ambiance, called gemütlich. Everything is slow, nice, and it's also known for the bear pit, where bears are actually in the city in a place, and you can go watch. The city, of course, that has a flag which has the bear in it. And you go to Bern and you immediately notice how nice the city is and how nice the environment is. Not really the city you would have expected this paper to be written, these papers to be written, and that's what we're going on now. In the old part of the city, in a house that was first built during the city's expansion in 1218, a story unraveled that was so groundbreaking and new that it still has effects today. Einstein lived in this house, and from October 03 to May 1905, during the 7 years in Bern, Einstein moved into 7 different places. For all practical purposes, this is his house. For all practical purposes, things did not go well at all. He had successfully finished all exams that allowed him to submit a doctoral thesis to the university in Zurich, but he had a hard time getting that thesis accepted. He, out of 3 people who graduated, 2 got assistantships, he didn't. So he had to do some job hopping around. And after he got married, of course, that was getting hard, because he had a child, 2-year-old child in 1905, and he really needed employment. That's where he found employment. This is the patent office, the Amt für Geistliches Eigentum, right there, just a stroll away from his house, where he worked from 7 a.m. to 6 p.m. every workday, and from 7 a.m. to 5 p.m. on Saturdays. Sundays were off. He did a lot of walks. His hobbies, of course, if you go to the upstairs room here, his hobbies were playing the violin, and his hobbies also were working on this, or his profession later was working on these amazing papers in these rooms. The Einsteins shared a kitchen and a bathroom with 4 families in this house. So this is, for all practical purposes, not the science star you would expect to write these kind of unbelievable science papers. In 1902, a French philosopher and mathematician, Henri Poincaré, wrote a book, La Science de l'Hypothèse, where he identified 3 fundamental problems that, in his opinion, were the most important to be addressed by the science community. One problem was concerned with the way light interacts with metals or propagates. Apparently, light ejected particles from these surfaces and in a way that nobody could explain. The second one had to do with the apparent random zigzag motion of microparticles in fluids, like pollen that make you sneeze in the spring, and when they were observed under the microscope. And the third problem had to do with the failure of experimental physics to show that the speed of light should depend on the direction in which it propagated. An experiment that, for all practical purposes, was a total failure for most theorists, done in Cleveland, just a few miles from here. By the end of 1905, Einstein had answered all of these problems in a convincing fashion, even though it took fellow scientists over 20 years in many cases to accept the conclusions that came out of these papers. We will now concentrate not just on what he wrote in these, focusing on 3 papers here, but also let's not forget how he wrote these papers. Einstein was not at a grand university like the University of Michigan. He was not even in a minor university. He was working by himself in evening hours, having a few scientists to talk to on his strolls to the Thunersee, 30 kilometers down the river, up the river actually, and really dealing during his day with mundane things like shower heads, like clock synchronizing devices, and things like that. What we want to do now is look in more detail at the 3 most important papers that Einstein wrote. And for all these papers, we had some people in Bern who made some experiments for us that we're going to show. Let's start with the photoelectric effect, written in March 1905, which was about light. In fact, the photoelectric effect that we're going to show is really a small part of this paper. The whole the paper that was written was so fundamental that it resulted in a Nobel Prize in 1921. In 1905, all physicists knew what light was, whether it came from the stars, from the sun, from radio antennas, or from lights in their labs. Light was waves that propagated and came to us just the same way as the sound coming out of my mouth comes to your ears. The sound is carried through air in this room. Light was not carried through air, obviously, because it comes through the vacuum of space, so it had to be carried by something. We're good in science to give things names we don't understand. You're going to notice that later in the talk. It was carried by something called ether that was carrying the light waves, and the problem was with this that the number of experiments really didn't work out. The experiment we're going to show here is an experiment that involves 2 light bulbs of equal strength. Same amount of power is coming out of these light bulbs. A metal plate and a device in the back that measures currents. Currents are nothing else than a bunch of negatively charged particles that are flowing from this plate through that device. Without any lamps on, the measurement device back there shows basically a really small current because the room is not completely dark. Then the red light was turned on, really small amount of increase. The blue light is turned on, blue light of being higher energy light. If you go to the swimming, go swimming in summer, you put sun lotion on because of the ultraviolet, which is closer to the blue and not the red. Because of that, enormous, much higher energy, and the current went up by a factor of 10. That was extremely hard to explain if you were believing that light was made out of waves, because as I just said, the same energy comes from both lamps, the red lamp and the blue lamp. The only way this could be explained, that's one of the fundamental aspects of Einstein's work, is if it's considered that light is really made out of little particles we now call photons. He did not do that, that came later. So if the red light is coming with 1 photon or many photons, as many as you want to, these photons do not have enough energy to knock electrons off out of that plate. And basically what happens, in fact, no electrons go to the device, the measurement device. If you, however, use the blue light, all of a sudden the energy is big enough, and the electrons are coming out with more, with a brighter lamp, more electrons are coming up, a higher current is being observed. The explanation that Einstein put forward only works if light is really made out of little particles. With the wave explanation, there's no way. The particles cannot bunch up. Each particle talks to an electron by itself. And that's the whole idea behind this, behind the photoelectric effect. What we're going to do here is show you just in the lab here, in this room here, an experiment that is very much identical to what Einstein, again, to show the photoelectric effect, but 1-to-1 here. What I have here is very simple. It's a metal plate, a lamp, And I have a device here that you could call a shuffle for negative particles. So basically, what I can do is by putting this shuffle on this plate, I can charge up this plate with negative particles. You immediately see that dial going up to higher voltage. We're actually measuring the voltage across this plate. So what happens is when the light, this is blue light, hits the surface, of course the electrons that I just dumped on there with my shuffle get taken out, and the voltage is eliminated. By the way, that happens to my spacecraft all the time in space. The UV light from the sun is basically knocking off negative charges, tending to charge the spacecraft in a positive way. That's exactly what had to be explained and what could only be explained if particles are really made out, if light is really made out of little particles. So the paper that Einstein wrote was a fundamental left turn on our understanding, or the previous understanding of radiation, of electromagnetic radiation as a whole. The theory, however, was highly controversial. In 1916, over 11 years later, a famous scientist called Millikan finally did all the experiments, and he basically found every single prediction to be correct that Einstein had made in his paper. And what he wrote in his paper, you can go pick that up in the library and look at what he wrote. And he said, despite the apparently complete success of the Einstein equation for the photoelectric effect, the physical theory on which it was designed to be a symbolic expression is found to be untenable. He did not believe it at all. Einstein's theories were still controversial in 1921, but only through the wise foresight of the Nobel Committee in Norway did Einstein get the ultimate recognition for the paper. What I want to do is now move on to the second paper that was written, the paper on which was the second grand challenge of Poincaré in his work I mentioned. This had to do with an experiment that was done over 70 years before by a person who worked with plants. And he looked under the microscope and looked at pollen, and these pollen were swimming under the microscope, going back and forth. And until Brown, this is called Brownian motion, because he was the first person who really looked at this and wrote the scientific explanation I'm just going to talk to you about. The Brownian motion was observed before, and many people had thought that these were little tiny organisms, little fish that went back and forth and kind of threaded in water. But what Brown noticed is if you actually put things in like little glass or some metal where you absolutely were sure there was no organism there, same thing happened. And what Brown did in his paper, in his seminal paper, he basically realized that this is a fundamental problem of water, of a fluid. It has nothing to do with pollen by itself. But nobody could explain how that worked. Einstein's view of the Brownian motion, which is kind of shown here in an animated way of one of these pollens, was straightforward. Einstein assumed that the pollen was roughly 1,000th of a millimeter. That's a small particle. But it was constantly bombarded by particles that were even smaller. In fact, the particles he calculated were so small that if the pollen was, if the particles that bombarded, the hydrogen particles, were the size of a baseball, the pollen was 1/2 mile in diameter. So these particles were unbelievably small, but so many of them were moving. Well, why does the pollen move? Every once in a while, of these billions of particles that hit it, every once in a while, billion of them are ganging up just randomly and knock from the left more than the ones from the left. And the whole pollen is moving over a little bit until just a few microseconds or milliseconds later, a billion particles gang up on the right-hand side, just randomly, because they move around like this and push it over in the other side. So under the microscope, what we're seeing, and this is what you perhaps had for breakfast in your coffee, this is milk. These are little, just a little balls of fat that are swimming and being knocked around by particles of water. Milk is basically water. And basically, these little motions you see were really an important characteristics of the fact that the way the water particles moved was in a statistical way. Until then, actually, the theory of gases, thermodynamics, was really a founded theory already, but nobody really believed that there could be deviations from its average behavior. The argument was always in classroom, there's so many particles, we'll always get what we expect. Well, that was not the case, Einstein said. If we go to small scales, things get out of whack. Every once in a while, things really don't turn out the way we are expecting it at the macro scale because of the fact that there are statistical variations. So this paper established two fundamental things. First of all, that matter is made out of atoms. Einstein was not the first one who came up with the atomic theory. In fact, the Greeks did. That's right. Atom is called an atom. But Einstein was the first who really put all the other theories to bed. Mach, in fact, one of the really famous scientists and philosophers of his time, basically said once he saw this paper by Einstein, he was totally convinced that fluids had to be out of matter, out of little atoms, which he didn't believe until that point. Einstein also established that these atoms interact in a random fashion. It's not predictable what can happen at the nanoscale, at the microscale. Things happen in a chaotic way, and sometimes things happen, very unlikely, but things happen if you wait long enough that you wouldn't have guessed based on its average behavior on the macro scale. Really important paper as well. The third of the experiments I want to discuss here has to do with one of the theories that puzzles generations of scientists like myself and some science amateurs, perhaps like yourselves. Has to do with special relativity. Paper is one of the most beautiful pieces of work ever written, in my opinion. Just like this Bach piece we're listening to. Really beautiful, based on simple structures, based on a few assumptions with enormous consequences, just like a Bach concert makes you feel after you're done. The paper really had to do with the propagation of light. And as I said before, the propagation of light before 1905 was connected to this virtual thing called the ether that was proven wrong by Michelson and Morley down in Cleveland. The idea was very simple. If there was an ether in the universe, the ether very likely will not be attached to the Earth, right? We already got rid of the idea that the sun went around the Earth and so forth, the Earth went around the sun. So why should the ether of the universe be attached to the Earth? So if I'm moving with the Earth this way, what should happen is I should go through the ether faster this way than perpendicular to it, for example. So if I run light this way, if light is going in, propagating in the ether, it should, move in a different speed than light going this way. It's just like sound from the ambulance that drives down the street. The sound changes as we go by because of the fact that the speeds change and so forth. Before, what Einstein did is he basically looked at this problem from a really fundamental point of view. Before I go there, however, let me just quickly introduce the concept of a coordinate system. Coordinate system for the purposes of this talk is basically a map in which two points are put into relation with each other. Coordinate systems can be put in different places. For example, if I'm centered on New York, a coordinate system centered on New York, Washington is approximately 220 miles in the south-southwest direction. Everything is pretty simple. I can move the coordinate system over. The distance doesn't really change between Washington and New York, depending on where I put the coordinate system. I can even put it on the sun, and the distance doesn't really change in our experience. What Einstein did, however, is he basically added one more variable to the equation, and that was the variable of time. Still very simple. I can put a clock in this room. There's a clock over there. There's a clock here on my table to make sure that I'm not cutting into the football game today. And the the times and the relation of space and time could be described this way. Well, Einstein said you could really look at this problem assuming two fundamental assumptions. First of all, the principle of relativity. The science we observe is independent of the coordinate system I observe it in. The science does not change because I look at the physics from a coordinate system, you know, from the bell tower down or in a car driving by on the road. The science doesn't change. A ball falls, the physics is the same. Principle of relativity. The second one is the principle of the constancy of the speed of light, which Einstein thought was inescapable. He actually always he went back and forth. The historical record is pretty interesting on whether the Michelson-Morley experiment actually drove this paper or not. And he actually made some 2 or 3 contradicting statements about that. But basically, the Michelson-Morley experiment, failure for the theorists, had confirmed that the speed of light was not dependent on the propagation direction of light. That's just as we said. What we're going to do is look at one of the effects of the this theory of special relativity, which really does nothing else than describe the geometry of that 4-dimensional space, 3 spatial coordinates and a temporal coordinate. And basically, in that 4-dimensional space, interesting things happen. What we're going to do is talk about experiments that starts millions and billions of miles away in a supernova that explodes. The particles that are accelerated in a supernova come across the galaxy, zipping at close to the speed of light, come into the solar system, fight against the solar wind that comes against it, make it to the Earth, and hit the upper atmosphere of the Earth. We're going to have 3 devices measuring right now these particles that come in. One is on Jungfrau Joch, I'll show you where that is. And the second one is in Bern, and the third one is right here. Jungfrau Joch is 3,000 meters above Bern. First I want to show you where Jungfrau is because it's really foggy there. I'll show you in just a second. Jungfrau Joch is right there in the middle between the 2 mountains. It's the highest train station in the world. You can go up there by train, and there's a research lab up there that does this kind of research. So this guy's refreshing all the time to tell you how many counts he sees. And basically what you see is a camera that's put on Jungfrau Joch. And basically what the camera sees are particles related to these cosmic rays. But the important aspect that I want to show here is as they interact, whole sets of particles are being made. And the particles we're most interested in here are particles that are called muons. They're kind of heavy cousins of electrons. But the important thing is that these particles only live for 2.2 microseconds. You can make a lab, you can measure this time. So because of the fact that the particles only live that long, if they propagate at the speed of light, the maximum distance they can propagate is 600 meters. So if they're made up in the atmosphere at like 4,000 meters, they can only propagate into the mountains, just hitting kind of the tops of the mountains. Muons can only make it to the top of the mountains if all they do is they live for 2.2 microseconds and they propagate in a classical way. On Jungfrau Joch, over here to the right, 60 of these particles made it in the last minute. They work perfectly well. The particles are arriving. The cosmic environment is showering them. But there's also 13 of these particles in Bern. They should not make it to Bern. They're 2.2 microseconds. If they move at the speed of light, there's no way, if they're made at around 4,000 meters, that they ever make it to Bern. And they sure shouldn't make it to Ann Arbor. Here they are. As you're sitting here, you're being showered by your galaxy, by supernovas far away. And this detector tells you what is hitting these 2 plates over there and are identified correctly as muons. The detectors over there are larger than the ones on Jungfrau Joch. That's why the count rate is larger. The detectors on Jungfrau Joch and Bern are exactly the same size. So basically what we're realizing as we do this analysis that in fact the particles are making it down, and even though they shouldn't. That's exactly what Einstein predicted. Something goes wrong here. When we add time and location together, like we did, the time of the lifetime of the muon and the total length it can propagate and the total distance it has to propagate, we put these two things together, things go wacko if you go fast. And in fact, what happens is dependent on how you look at it. Now let's sit in Bern or in Ann Arbor, however you want to, and ask, why do the particles come to me? I know for a fact I can take a laser and measure the distance to Jungfraujoch from Bern, and I know for a fact at 3,000 meters. I also know for a fact in Bern that the speed of light is constant. The second assumption of Einstein's theory. Well, something has to happen with the time. As I look at this muon, as it does its 2.2 microsecond, the time that I'm observing at Earth is way longer. Time is relative to me as an observer in Bern. It dilates. One of the major conclusions of this paper. Well, we can also play muon. Let's sit on the muon and come down, sipping from the atmosphere at close to the speed of light. Now, what I know are two things. I know I'm going to live for 2.2 microseconds. And I also know I'm going with the speed of light. Speed of light is constant. The only way I can make it down there, remember the physics has to be the same. In both coordinate systems, I have to make it to Bern. The only way I can make it down there is if in fact the distance I have to travel is way shorter, length contraction. Those are the two ways of looking at it. You assume that nature that the principle of relativity holds. You assume that the speed of light is constant. Two things can no longer be the case. It cannot be the case that time is absolute. It matters how you measure time and how you look at the time from a moving or a stationary clock. And it's also no longer true that space is constant. The fact that I can measure the location between New York and Washington independently roughly of how the coordinate system works is just because nobody's moving fast. In September, roughly 100 years for actually today, pretty much, the final paper was written of that year, which had to do with the most famous equation, namely that mass and energy are equivalent. The speed of light is constant, so basically we just have the wrong units. That's why there's a speed of light there. Mass and energy are equivalent. It's an unbelievably important equation. In fact, the most famous equation, the best known equation in the world, in any poll people are doing. What we want to do now is move on and basically go and ask what happened to these papers in the present. All right, our friend Dave. All right, the photoelectric effect. The impact of the photoelectric effect is just amazing, and what I want to do is just use one example in hospitals. What I'm going to show you is the operating room in one of the hospitals in Bern. This is Professor von Fischer on the right, and what he's demonstrating is the use of an infrared laser that he's using to do surgery on an apple, because I thought he couldn't take anything else on empty stomach. And basically what you see is the red thing you see in the apple parts that come off is not the laser he's using, it's just the guide laser, the infrared laser you cannot see with your eyes. And what he's doing is basically demonstrating that on this apple he can make really accurate cuts, and even he knows E equals mc squared. And basically what he has developed with that laser is a way to do breast surgery in a way breast cancer surgery in a way that is far less damaging than a regular scalpel. just one of these tools that came out of the fact that, that photons, that light is made out of photons. In fact, Einstein later in 1918 wrote a paper that basically provided the foundation of stimulated emission that is at the heart of the laser. There's a lot of other things that we use in hospitals today that relate to that. When I was a kid, and I'm not that old, we used to measure fevers, under the arm. Remember how it took like 2 minutes, felt miserable anyway, and it took forever, and your parents said you have to keep it there. Today, it takes 2 seconds, one of these things you put in the ear, originally developed for NASA. Again, one of these things that only works if light are photons, because you're looking at the actual transition line from a thing. What I want to show here is one of the things that's worked on at the University of Michigan. University of Michigan is the first university to develop a femtosecond laser that is used in commercial applications. A femtosecond relates to a second, like 1 second relates to 31 million years. It's a pretty short time. And the University of Michigan researchers in various departments here at physics, but also in engineering, up where I work, have developed applications of these lasers, and one of the most amazing applications has to do with eye surgery. We really don't want scars in eyes at the surface of eyes, and basically these femtosecond lasers, they're so accurate that basically the scarring is, for all practical purposes, eliminated. And basically this is one of the breakthrough images. This is an image of one of these cuts, an image that is now being used, in an application that's now being used and is used for commercial applications. Amazing impact of photoelectric effect. The Brownian motion really has put our focus on the small. What I want to do is kind of show you what the small stuff is we're doing. Well, you can look under a microscope and see down, but you can look even lower down and look at an invention. Look with an invention that is called the electron tunneling microscope. That is basically consists of a small tip made out of just a few atoms that is moved around the landscapes of the atomic landscapes. And basically, electrons jump back and forth that are measured, the tunnel, as we call it, are measured and amplified, and so we can kind of move that tip up and down really calmly and image the micro landscapes that are there. This is platinum, same material this ring is made out of. Let's just think what we're looking at. If you stretch this ring from Los Angeles to Washington, just assume you could stretch it. The distance between two of these bombs is that big, ½ an inch. In that scale, a hair is 2 miles. The thickness of a hair is 2 miles. So the landscapes we see is enormous. There's a lot of space at the bottom, to speak with the language of Nobel Prize winner Richard Feynman. This is with imaging device like this at less resolution is a part of a computer chip. This is an image of 3 gadolinium atoms, and actually what's measured underneath it is the electrical conductivity of these atoms on the surface they are at. So we can do experiments at atomic scales. Just the most amazing to me. But these things, these micro devices and nano devices are now used everywhere. You use your printer today. These are the kinds of parts that are in there, highly magnified, that are using nano and micro technology, enabling to cheap printers. So you don't have to go to the print shop like we used to, with a week's notice. Remember that thesis. This is another invention that is really quite amazing. It's what you see coming from that tip is a carbon nanotube. These nanotubes can be as thin as 10 atomic radii in diameter, and they have unbelievable properties. The name of the game is to make many of them and put them together so they work as a macro volume. What you see is a whole carpet of carbon nanotubes that were manufactured. Here you see somebody who managed to do kind of a crosswise structure. If we advance this will have unbelievable applications for aerospace industry, satellites, or for your cars. Because at roughly 1/8 of the mass, it has 100 times the strength of steel. So the applications of that, we can only guess today. At the University of Michigan, devices are developed, and they have MEMS on them like they should. Devices are developed that do amazing things really small. This is a MEMS device, a mechanical device that can basically measure DNA on a chip. If you ever go to a hospital and ask them to give you to show you the room where they do DNA analysis, they show you a device that's like bigger than a refrigerator or even bigger. This is on a chip. It's not quite working like the refrigerator yet, but we're getting there. It's amazing work, again, done mostly at the College of Engineering, but also in collaboration with people all over campus. Special relativity has opened our eyes to the fabric of nature, and we're using it every day. I travel. I want to understand Mercury orbit. The orbit can only be understood with these applications. I fly by Venus. I look at the Earth. GPS sensors today. One of the major perturbations that need to be put in the propagations of these models to make sure that your directions in your car are correct are relativistic applications. I want to go to Mars. I want to use a rocket and land carefully. The calculations that are going to go in that are all used special relativity. I can ask important questions and basically ask, well, how old is the universe? I can start digging here. And this is one of the ways you can figure out. This is Buzz Aldrin as he came out of the capsule and unwrapped an experiment that is basically an aluminum foil. First experiment on the moon. And that foil stood there and collected solar material. When Buzz was done with this other stuff, he wrapped it up, brought it back home, and that's what, for example, I did for my thesis and others, to look at the composition of these particles. With some theoretical understanding of how the sun works and so forth, we can learn a lot about the age of the sun. However, what can we learn about the age of the universe? What are these interesting and most amazing objects that are around the universe that we can observe if we look at the night sky, or if we look even at the night sky with different telescopes? Well, these particles, these photons that come from the deep universe to us, come so through not a flat space, but come through from a really, come so affected by the bodies in there. And this is in fact what made Einstein a star. That experiment that was done by Eddington, that basically showed that during an eclipse, radiation from light from a star was ever so slightly deflected because it passed nearby the sun. And that deflection of light can be used now to explore the deep universe. There's weak lensing, gravitational lensing, strong gravitational lensing. There's specialists here at the physics department in astronomy that do this for a living. It's an unbelievable active research area that uses these effects. The effects, of course, that were predicted in a paper that Einstein himself wrote roughly a decade later, after the 1905 paper, that basically explained all this due to the fact that not only was space and time interchangeable in a certain way, like we just showed in special relativity, but once you put gravity in, things become even more exciting, and space curves, and interesting things happen to the propagation of light. What we can do now is stand even further back and ask about the history of the universe, about where galaxies come from. And interestingly enough, the very paper I just showed you provides some of the answers to that. Einstein had a hard time with this, though, because he really thought the universe should be totally not dependent on time. So he put in a solution to the universe, to the equations. Actually, Einstein didn't do this solution himself. A Catholic Monsignor called Lemaitre and a Russian scientist called Friedman did the calculations and showed that the very equations that we just used to show the deflection of light predicted that space should expand. They expand almost like some explosion happened years ago, many, many years ago, 15 billion years ago or so. But that's really not what happens. Space by itself is expanding, just like if I blow air into a balloon. Points on a balloon are moving, I can draw on a balloon, are moving away from each other. That's exactly what we're observing in space. Now, this expansion can be followed back in time by using modern observational techniques like the Hubble Space Telescope. And one of the most amazing facts is that the expansion is not slowing in any way. It's speeding up. One of the most amazing observations in the last 5 years. And it leaves it at one of the most embarrassing times physics has been in my opinion. This is what we think the universe is made of today. Heavy elements. All of us are made of heavy elements, basically. Oh, guys, we're not really typical for the universe. We're up there in that green sliver. Well, there's also neutrinos that have been sipping through you the entire talk here. You didn't even notice. There's stars. Well, you know those. There's free hydrogen and helium we can observe using some other techniques. But wow, much of this pie chart is blue, which means we have no clue, but we have names. One we call dark matter. Dark matter is stuff that interacts with stars and other galaxies through gravity. Dark energy is that very force that accelerates the universe. We don't know what it is, but we know what it does. We look out the window in fall and we see the leaves move. You don't know whether there's wind there, but you know it moves the leaves, and your experience, your scientific intuition says there's wind there. We don't know what dark energy is, but we know what it does. It accelerates the universe. We can describe it through its actions. And this is important research that has to happen now, and important research that is happening and is going to be reported on in this series. I want to close the loop. Go back to Bern, where we started. And basically tell you that all these people that stroll around Bern have been affected by what was written in that little room in the old city. Now we're going to look down into the bear pit. And you see the bears play. The kids come there to see. They hold devices in their hand that were affected by what was written in 1905. We look at the beauty of nature and we look beyond the horizon. And we look back and ask what happened 100 years ago. What happened 100 years ago is that through a series of papers, nature became more beautiful. We understand the fabric of nature in a way we haven't before. And nature has always been that beautiful, but we understand nature in a more fundamental way. I also stand here today, 100 years later, and I say, we are in a similar place today as we were in 1905. A person, not Poincaré, somebody else could write a paper today and point out 2, 3 of the most fundamental problems we have. Dark energy, dark matter may be part of this. But we have no clue today. And we have many young people here today. Remember, Einstein was 26 years old when he wrote this paper. It's up to you to make that impact and solve these problems. Thank you.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.